All right, today we're going to talk about frames a little bit, but mostly beams. I have a little diagram of a beam set up here, or a sample of a beam set up here. But we're going to start with frames first because there's one more little connection type that we didn't really talk about, at least not yet. And it would be useful because it's not obvious necessarily what to do with it. So I'm going to set up a simple frame for us to work on that has this kind of connection, and then we'll get into the more specific things about beams and flexural stress and all that kind of thing. So here's the frame I want to work on. We're going to put a pin down here, and then we're going to put a member over here. I'm going to draw this one a little bit different. I'm going to have a little section in here that sticks out, and then I'm going to do the same thing on the other side. This piece is going to have a slot in it, which we haven't really dealt with yet. So inside this slot there'll be a some little opening like this where a roller or a wheel could roll back and forth in that slot. We're going to go ahead and also pin this in, which is also a little bit unusual for us anyway in this course, to have two pinned connections, because that would generate 4 reactions, which with just pure statics we won't be able to solve all of those. So there must be something else going on in this problem. Let's add another piece here. Something like this. All right, and we'll pin. That's got this is going to be a slot, and it will be frictionless. We're not going to deal with friction in this course really at all. And we would have some kind of force, maybe a force over here. Let's make that 750 pounds just to have a number on it. We'll put dimensions when we need them, but for now we just need to know what to do with this slot. So this idea is that you've got basically a surface, this surface here, or the one inside here. I'm talking about these inner surfaces here, so either that one or that one, and this little wheel inside here is rolling against one of those surfaces. So we're going to treat this just like we treated the rollers earlier, when we had this guy out here, and we just said that, hey, this roller is allowed to roll along some surface, but it can't go through the surface, but it can go parallel to the surface with no reaction, but the reaction is perpendicular to the surface. So if the surface is right here, we're going to treat this like a roller, and it can move up and down, but it can't move perpendicular to the surface or the inner surface of this slot. And it doesn't really matter if we're talking about the top inner surface or the bottom inner surface. The reaction is still perpendicular to that. So the reaction is somewhere along that line. We don't necessarily know if it's pointing up and to the left or down and to the right, but we know it's on that line. So if you're presented with something like this, you could attempt to find your external reactions. If this is A, put some letters on here so we can talk about them. So AX and AY, EX and EY would be our external reactions. You could solve for some of those. You could solve for the 2 Y reactions by writing moment equations, but you couldn't solve for the X, EX, or AX reactions with just statics. So that kind of tells you that, at least in the context of this course, there must be some other thing going on. So if you ever get to that point where you've got all the external reactions you can, the next step is to take individual pieces and look at the individual pieces. So I would take member BDF, although you could do ABC, or you could even do CDE, although that one's not going to help you in this particular case. So let's do BDF. Draw it. just it. So we have the free body diagram. There's B. Here's D somewhere over here. And F is just where we applied that force of 750 pounds. At D, we have two members, CDE and BDF. They're both connected at D. Neither of them are two force members, so the best we can do at D is to draw a reaction in the X direction and one in the Y direction. But at B, since we know this thing is acting like the rollers that we've been using, we don't have to draw BX and BY. We can draw just the force at B. And we make it perpendicular to member ABC, so something like this. And we pick a direction for it. And just call it the force in B, or the force at B. We actually know its angle, assuming I give some dimensions to the part up here. Let's say that this is 1, 2, and then this hypotenuse would just be the square root of 5. So if the member ABC has a rise of 2 and a run of 1, then perpendicular to that would just be, transpose those. So a run of 2 and a rise of 1, the hypotenuse still stays the square root of 5. That's a 2. It kind of looks like a 3, but that's a 2. And we'll zoom in. Now I've got a free body diagram with 1, 2, 3 unknowns, one known value, and some dimensions. We can put some kind of dimension, 25 inches and 10 inches over here. So we have a free body diagram. We could put our coordinate system in there if we wanted to, x-axis, y-axis. And depending on what you're trying to solve for, you're trying to solve for the force in B or the resultant at D or all of it, would kind of dictate what you should do next. But in general, you need to write a moment equation. Either a moment at D would find you the force at B, or a moment at B would find dy. So one of the parts for the resultant at D. Let's do the moment about D just to finish out this problem and make sure we all agree on how we would go about doing that. Probably have to zoom. Yep, there we go. So I'd say clockwise moments about D equals 0. 750 pounds times 10 inches would give me inch pounds clockwise. Dx and dy line of action goes through point D. So does the x component of FB. So those don't enter into my moment equation, but the y component does. And it's going around counterclockwise, so that's a minus for my equation. So minus, I only want the y component though, FB. Y component is 1 over square root of 5. And its moment arm is that 25 inches. And we can solve for the force in B. Is just going to equal 750 times 10 divided by 25 divided by 1 over the square root of 5. 670.8 or so. And let's see, does that come out? Oh, let's see, counterclockwise, clockwise, so those work out. FB looks like it is going this direction. We do get a positive number here. And that would be pounds. And the positive sign here means that we chose the correct direction for this arrow. If we got a negative, then the arrow should have been going the other way. At that point, you could do summation of forces in X and in Y to get dx and dy if you wanted them. But I just wanted to show how you might deal with these slots. There is a similar one. We'll just draw maybe over here. That works the same way, but looks different. So it might look something like this. And there might be a rod here, and you might call this a slider or a sleeve. And again, you're looking for something that's frictionless in general, but this thing could be connected to, might have to be pinned to, remember BDF, and it does the same thing where this rod, you know, goes through a hole through the middle of this slider or this sleeve, and this has the same idea where it's constrained to move in this direction, so that it doesn't have a reaction other than whatever friction you might apply to this rod, but it can't move in this direction, so it exerts some kind of reaction force perpendicular to the rod. So it would work just the same as this. It's just a different type of mechanism. So just wanted to point those out, the slot, slider, or sleeve, and how they might be used in a frame to connect things together. All right, so enough of that. Let's go on to beams. So all of the frames have something, at least one piece, that might be thought of as a beam, but a beam doesn't have to be in a frame. It could just be a beam on its own. The main thing with beams is that they flex, and we might think of flexing as bending. So where previously, when we just had axial forces creating axial stresses, the object, whether it's a beam or whatever, if we pulled on it, pulled or compressed on it, the force was either a tensile axial stress or a compressive axial stress, and it was easy to calculate it. It was just the internal force divided by the area that force acted on. Beams, they do have a similar stress. They have a flexural stress or a bending stress. But it uses a different equation. Same variable though, sigma is still going to be the name of the variable. Negative m times y over I. And that negative is part of the equation just so that some of our measurements later on will produce tensile forces with positive signs and compressive forces with negative signs. And for that to work out, we need this negative side as part of the equation. All right, so these terms are unfamiliar other than y. Y is a distance in the y direction. But m is the internal. Again, we're talking about internal stresses and strains, although we're not talking about bending strain. So internal bending moment. We haven't really done a lot with this, but it's similar to those concentrated moments that we had at the fixed supports. It's not the same, but it is at least similar along those lines, where there's something inside the beam that is trying to flex the beam. And we're going to call that this internal bending moment. Y is a distance measured from, for now we're going to call it the centroid until we have some more terms to work with, from the centroid of the cross section of whatever beam. So this is our beam and we've got some kind of load on it here. Then we look at the end of it to see the cross section right here, and we're talking about that cross section. So the measured from the centroid of the cross section of that beam that we're flexing, and it's measured from there to wherever we're trying to calculate the stress. So that'll make sense more later. And then I is moment of inertia for the cross section. So this will calculate similar to the way we calculated centroid locations. It's a similar approach. Or we'll just look it up. You know, maybe we're dealing with a beam that's pre-manufactured and we just look up the moment of inertia for that beam. Or we can use integral methods to calculate it, also similar to how you did with the centroids. In general, we're either going to look it up in a chart or we are going to use a process to calculate it from primitive shapes, a composite shape. All right. We're mainly going to deal with two types of beams, two categories of beams. One of them is going to be called simply supported. So here's our beam. And it's going to have a pin somewhere and a roller somewhere. And we're going to call this one simply supported. And then the other kind of beam that we'll deal with is going to look similar, except for the way that it's supported. And it won't be not simply supported. We're going to call this one cantilever beam. And it's going to have some place, put it on this end, where it is using one of those fixed supports. So remember when we had the frame with the pulley and the rope, we used a fixed support. A cantilever beam will have a fixed support. So it might be embedded in a wall like this. It might be bolted. It might be welded. But it's fixed here where it's not using a pin and a roller combination, but it's using some sort of fixed support. I've drawn these horizontal. Beams do not have to be horizontal. That's just, it works nice on the paper when they're horizontal, but they can be at any angle with these supports, you know, however they need to be. But a lot of times you will see them horizontal, but they do not have to only exist in a horizontal orientation. All right. So let's get a new sheet of paper so that we can look closer. We'll just look at a simply supported beam, but we can look closer at that. All right. So I'm going to use this for the time being, then we'll draw some. So like I said, it'll have a pin and a roller. Let's put it up kind of close to the top. So the pins and rollers don't have to be at the ends. They can be, you know, wherever. A lot of times you're going to see them drawn at the ends of the beam. We'll have all sorts of loads on here. A lot of times there'll be point loads, distributed loads. We could even put a concentrated moment on here where you draw the curved arrow. For today, this is just the introduction, so we are going to just deal with a point load, probably just one point load in fact. But this would be a beam setup for a simply supported, so there's a pin and a roller. There's some amount of loading, a point load in this case, and it is a, in this case, rectangular beam, but we might imagine it as an I-beam or something like that. And what we're trying to do is determine if we had this beam and we pushed on it enough, then it probably is going to deflect. You know, it's going to bend, something like that. Now, we don't know yet exactly where this bend, you know, or what it's going to look like. We might have an intuition about what it should be. Later on, we will actually calculate the entire curvature of this beam and be able to tell where it's going to deflect, what this deformed shape is going to look like, and all of that. But for now, we just have an original axis, and then we have some amount of change when we apply enough force. So let's draw that so we can draw on there. Just put our beam. Let's use this as an I-beam so that it's one that we can just look up. It's simple enough to deal with rectangular beams, but I want to show you how to use the chart a little bit too. So I want to draw this one like an I-beam from the side. So there's kind of the top flange. This will be the bottom flange. And then there's the, so it's a beam like this, but it has flanges, you know, like there would be a top flange and the bottom flange for those things, where we're drawing it from the side. So if we looked at it from the end, you know, if we looked at it from the end, then it would look something like this. Something like that. And it would have this eye shape. Let's give this one a specific name. Let's say that it is a W18 by 97. So remember, these letters and numbers mean particular things. So the W is talking about that the shape here, just the general shape. So W is wide flanged I-beam. The 18 is called the depth of the beam. It is the distance from the very top of the flange to the very bottom of the other flange. In this case, in inches. This is the nominal depth, though. To get the actual depth, we'll have to look up in a chart, but it's around 18 inches. And this guy is the weight per unit distance. So in this case, pounds per foot. So in other words, if I took 1 foot of this beam and cut it off, that it would weigh 97 pounds. So this is a big beam. It's 18 inches. Well, it's actually, if I look at the chart, let me show you the chart too. So here it is over here, down here, W18 by 97, down at the bottom, or near the bottom. It has a depth of actually 18.59 inches. So there you can see the depth as it would be if you took a ruler and measured it. Has some other, like width, how wide the flanges are, how thick the flanges are. Oh, this web, we haven't talked about a web. So over here, we have mentioned flange. Also on top, there's no difference in the top or bottom flange on an I-beam. This part in the middle, that's the web. On a T-beam, that's called the stem, but on an I-beam, it's called the web. So it gives me some dimensions for those. It gives me the cross-sectional area if I need that. Then it gives me 6 columns over here, 3 of them under this heading of XX, and 3 of them under the heading of YY. So, and it gives me this graphic at the top that shows where XX and YY are. So XX is this horizontal line, and YY is this vertical line. Those are 2 different axes, two different orientations, and you use the one that is perpendicular to your loading. So in ours, we haven't drawn any loading on here. Let's say that we're going to load it this way, and we'll pin and roller at the ends. So here's our beam. Now this is not an I-beam, this is just a rectangular beam. But if I look at the end of it, then the load would have been something like this. Kind of hard to see when you're looking at just the end of it, right? But the load would have been there somewhere. And I want to pick the axis that is perpendicular to this load. So that axis would be this way. So kind of like that. So matching up with our chart here, that would be the XX axis. If, to get to this YY axis, let's go back to here. Here's our load. I'd change the load to go to the side of the beam. So I'm like pushing on the side of the beam. Now when I look at the cross section, here's the cross section, the load's this way. Perpendicular to that load is this axis, which they had lined up named YY. So all of that to get to which one of these sets of numbers am I going to use. So I'm going to use the XX, and most of the time most of the time the charts are built in a way to where the ones labeled XX are the normal orientations for, I mean average orientations for how these beams are intended to be loaded. So in this case, XX is perpendicular to our loading, and here is I right here. So there's the moment of inertia. So we just go to W18 by 97 because that's the beam I said we were using, and we read 1750 inches to the fourth. So we just get a value for I. So I just wrote it down from the chart. So that's one way to calculate, well, not calculate, to obtain the moment of inertia for an I-beam, is to look it up in a chart. Next time on Wednesday, we'll actually go in and calculate moments of inertia from primitive shapes, similar to how we did centroids. Let's put some forces on here. Let's say that we had a pin over here, a roller over here, and a force somewhere over here. So we're going to replace the pin and roller with just reactions. So this will be the AY reaction. We'll call this BY. There could be an AX. You know, it's possible with where the pin is. But I don't have any other forces in the X direction, so this thing is just 0. So I don't have to worry with it. Let's put, this is a huge beam, right? 18 inches, 100 pounds per foot. So it's a massive beam. We're going to have to put a lot of force on it to do anything to it. So let's put 20 kips. So 20,000 pound point load here. I don't know what that is that's causing that, but there's something that we think is 20,000 pounds that is more or less concentrated at this point. Let's give some sizes here. Let's make this 20 feet. Oh, except I don't like having the 20 and the 20, but I guess I already did it. And then we'll make this one 10 feet. Okay, that's feet. That's another marker for feet. All right. So at this point, we could solve for AY and BY. We don't know anything else to do, so we might as well do that. I'm just going to solve for AY. So I'm going to do moments about B. Clockwise moments are positive. So I've got a negative, because this would go around counterclockwise. Negative 20 kips times 10 feet. This AY would go clockwise, so plus AY times, and that's 30 feet. Okay, so this equation we can solve for AY. And it comes out positive. So 20 times 10 divided by 30. Whoops, 30. 6.67 kips. All right, and we could get BY by summing forces in the Y direction, but what I'm going to do, we're not going to need BY. All right, now we can expect this beam to bend, you know, kind of like, well, I can't really push on it, but something like that. Let's draw. If we originally had, before we put the 20,000 pounds on it, some kind of axis like that, a kind of longitudinal axis for this thing, then when we apply the 20,000 pounds, that axis is going to do something like this. You know, this is much exaggerated, but it's going to bend down. It's going to bend. The maximum deflection won't necessarily be directly under the 20,000 pounds. We'll worry with that later when we get into beam deflection in general. Right now we're still introducing just flexural stress. The other thing that happens here is, let's take a little piece of this beam and draw it, but let's draw it deflected, curved. So let's just take a little piece and exaggerate what it might look like when it's curved. So here's that axis that's going through it. And look, it's not an optical illusion here. I had to draw this line much longer than this line to make it curve this way. So I had to stretch out this line or lengthen it. Same thing happens to the actual fibers, if you want to call them fibers, in the beam. The ones on the bottom here, they're having to stretch. The ones on the top are getting shorter. They're having to compress. And if I drew, maybe, let's take the center line here. These bottom fibers, they are stretching. These top fibers, I'm going to show this as a opposite direction, as a compressive force. And you would have some sort of relation like this where you have maximum tension down at the bottom here and maximum compression at the top. Now, top and bottom are not always true. So like in this case, maximum tension's on the bottom, compression's on the top, but if you bend the beam the other way, then now the maximum tension's on the top. So it's not always that tension's on the bottom. But if I remember way back, where'd I even write it? Let's see. Here it is. Way back over here, with this equation, we said that we put this negative sign in specifically for, we wanted tensile stress numbers to be positive and compressive stresses to be negative. All right, that's fine. So tension, we want to be positive. Compression, we want that to be a negative stress. So it doesn't matter what the numbers are. If this is a +1 and this is a -1, to get from plus to minus, somewhere I have to go through 0. And that happens, that transition happens at this line, this axis. This so happens to correspond to the centroid. So if we draw our, let's draw our cross-sectional view a little larger. So this is my cross-section of an I-beam. So the centroid of this, if we had drawn it perfectly symmetric and everything, you know, and maybe you had a template or something, then the centroid of it would just be somewhere right through the center because it's symmetric. So the centroid would be right here. If I draw this axis, also this XX axis on the screen, that is called the neutral axis. And in this case, all the stress below the neutral axis is going to be a tensile stress, and it's going to get larger and larger and larger the further away I get from the neutral axis. In fact, I'm going to measure a distance from the neutral axis, and I'll call that Y. And that's this Y in my stress equation. So I could, this would actually be a negative, right? If I'm measuring, if this is my reference and I'm measuring downwards, this is actually a negative value. If I were to measure from the neutral axis up to the top, where this maximum compression is, then I would have a positive Y. And looking at our equation, a negative Y combined with a positive M, which we're not worried about the positive and negative on the M yet. But there's this other negative sign. So a negative times the negative Y gives this a positive value. Moment of inertia is always positive. M is positive and negative depending on the direction of bending, which we'll worry about later. For our case, this is a positive M. And then Y is a negative number. So this whole term would come out positive, which would give a positive stress. if I measure from the neutral axis down, and this is a negative distance. And that corresponds to having a positive value for the tension on the bottom of the beam. All right, so we have I in our equation here. Let's write our equation so I don't have to keep flipping the pages back and forth. Here's our flexural stress equation. Sigma equals negative M times Y over I. So we have I. It's right here. We have Y. It's right here. We don't know exactly, but we can calculate it. Remember, I didn't write it down, but we had the nominal depth of 18 inches, and we have the actual depth 18.59. So this is the depth, 18.59. So Y is just half of that, so whatever that is. Oops, hold on. 18.59 divided by 2, 9.295. Negative because I'm measuring from below the neutral axis, so that gives me a negative Y. I just need M. So I have Y, I have I need M. So how we get M is, there's a couple of ways. How we're going to do it right now goes back to this, and we are going to pick a location along the length of the beam that we want to know the stress. So for now, that's how we're going to do it. In a few days, we'll be able to figure out where the maximum stress is. But for now, we're going to say that we just want to go to the middle of the beam, cut it open right there. So the middle of this beam is 15 feet. So cut that beam open, chop it in half, look at the end of it, and see what's going on there. It should be an I shape because we're dealing with a W beam, so it's a wide flanged I beam. And see what stresses are in there. Or not stresses, we'll get to the stress. This is the stress. What forces and bending moments are in there. So let's do that. We've already found AY somewhere, 6.67 kips. Let's cut our beam, cut it open, draw this side, although we could draw this one, but I'm going to choose this one, and draw that free body diagram. So we'll put it over here. So here's the top flange. Here's the bottom flange. And we cut all of that side off, right? So it's only this side. So there's AY. So we have a point load here that is 6.67 kips. So just looking at this free body diagram, in order for this thing to be in equilibrium, right now it would want to move up because I'm pushing up on it. So there's a force pushing down, and that force has to equal 6.67 kips in order for this to be balanced. So the summation of forces in the y direction is 0. I drew this one with a half arrowhead, so a single-sided arrowhead, and that's on purpose. Remember, those single-sided arrowheads are shear forces. So this is a shear force. And this is the internal shear force that is trying to go in and basically shear this beam in half at that point. That normally doesn't happen. The only time that kind of might happen is if you put a massive point load very close to your support, then it's possible that you generate enough shear and there's not much distance between where it can't move and where the shear force is, and you might shear, something like right there, you might shear it off. But normally the shear is not the mode of failure that we're going to be interested in, but it is there. Now let's say this is my little free body. That's almost perfect. If I apply these two forces to this, whoops, can't see. If I applied these two forces to the shear force on the internal shear force and the reaction at A to this free body, it would do this. So it would spin in place. It wouldn't move up and down because it's balanced in Y. There's no forces in X that we're looking at right now. So it would do this. So there's something that's keeping it from doing that. And that something is the internal bending moment. And we're going to draw it like this. So this guy is the internal bending moment that goes into our bending equation, or our flexural stress equation. Okay, now it's easy enough to calculate it because remember I cut this beam at 15 feet. So I know this distance. So I can take a point right here on that surface where I cut and do the summation of moments because I know that this body is not spinning about that point. So that means the moments have to be equal to 0 about that point. I'll just say clockwise moments are positive. Now, I didn't randomly choose this direction. This is the one time where when you're drawing a concentrated moment, you have to draw it in a certain orientation. So if you are drawing the left-hand side free body diagram and you've cut it on its right, then you have to draw the internal bending moment as a counterclockwise moment. If we had taken and drawn this side, and we're drawing the internal bending moment, you have to draw it as a clockwise moment. And that's only so that later on when we're drawing diagrams that we all agree on what's positive and negative. Otherwise your diagrams would be inverted from mine. So we do have to agree that if you're drawing this free body diagram where you've cut this piece, you draw a counterclockwise moment. If you're doing the other half, you draw a clockwise moment. And then you solve for is it positive or minus or negative. So here I'm doing moments about this point, I think I'm gonna fit it here, 6.67 kips times 15 feet. Minus, because I said clockwise is positive, this is drawn counterclockwise, so minus m. And there's no multiplying times feet or anything. It's moments enter moment equations as just plus or minus. So I can solve for this. And it's just going to be 6.67 times 15. 100, and we'll call it 0.1. That'll be foot kips. So we do have to keep in mind that's not pounds, that's thousands of pounds. All right. So now we've got all of the pieces that go into our flexural stress equation. All we have to do, and we need a new sheet of paper to do it, is to write this equation with the variables plugged in. All right. So sigma flexural stress equals negative m times y over I. So equals negative m. We calculated a positive m based on our drawing of this internal bending moment. Oh, foot kips. I don't know what I'm writing there. Kip. All right, so this is going to be times, this is feet, and all these others are in inches. This is inches to the fourth, this is inches. So we need to convert 12 inches per foot. And then let's go ahead and change our kips to pounds. So 1,000 pounds is 1 kip. All right, so all of that just to convert this over to inch pounds. times y. So we have to decide, are we trying to calculate the stress at the top of the beam or the bottom of the beam or some point in between? Normally, you want to find the maximum stress. In this case, the maximum tensile stress is on the bottom, maximum compressive stress is on the top. And normally for steels, ductile materials, it doesn't matter if you're talking about tension or compression as far as failure goes. So I'm just going to, since we have this one labeled as going to the bottom, I'm going to put negative 9.295 for the y value. So times negative 9.295 inches. And then the denominator is I. We looked that up quite a while ago from the chart, 1,750 inches to the fourth. So we should have we already canceled the feet out. Feet cancel out, kips cancel out. I've got inches, pounds, and inches. So pounds times square inches on the top, inches to the fourth on the bottom. So that's pounds per square inch, which is PSI, which is a measure of stress. So it looks like we've got all of our units working. We just need to put our numbers. Oh, and the negative and the two negatives become a positive when we multiply them together. So we do end up with a positive number. 100.1 times 12 times 1,000 times 9.295 divided by 1,750. And it's not that big of a number. 6,380.1 PSI. We can take that number and compare it to the strength of whatever this material is. Now, most beams are made of steel of some type, and most steels don't even begin to yield until 30,000 psi. So, and we're at 6,400 psi. So we've got plenty of headroom before we even begin to yield most materials that a beam of this size would be made from. But remember, this is a gigantic beam. It's 18 inches tall or deep and 30 feet long. So this thing weighs, 100 pounds per every one of those feet. So it's 3,000 pound beam, 18 inches. So it's a massive beam. Even though we put 20,000 pounds on it, it did not, at least at this point. So this is only the stress right here. Right there. That's the stress we just calculated. There could be some other point somewhere else that has a bigger stress. There'll be a lot of points that have a smaller stress. So that is one thing with this method. When we cut the beam at a specific location here, and then we chose a specific location by selecting the Y value, we're just calculating the stress, basically the stress on this bottom flange at this point in the beam. So that's the only stress we calculated. So we do need some methods to figure out, is that the worst stress in the beam? We think it's pretty bad, but is it the worst stress? Is there going to be a stress that's large enough to cause the beam to yield? So next time we'll get into how to figure out where in the beam is the worst possible stress. But we're not ready for that just yet. This is what we should be comfortable with right now. Just the idea of beams in general. This idea that there's some point on the beam where if it's flexing, there's zero flexural stress because it's transitioning from tension to compression, and as it goes from one of those to the other, that transition point is actually zero flexural stress. Need to know a little bit about how to read these numbers, how to look in a chart like this and pick out, am I supposed to be using this set of numbers under XX or under YY? I think those are, and maybe how to calculate a moment if you specifically cut a beam at a certain location. How do you find the moment there? And it's usually just doing the summation of moments about that point that you cut open. Okay, on Wednesday we will look some more at beams and some more techniques for figuring out this bending moment. and maybe we'll get into figuring out where is that maximum stress going to occur. So more of the same stuff. Also, we need to calculate moment of inertia, not just look it up from a chart. So we've got a few more things to add to this, and we'll add some of those on Wednesday. All right, we'll see you then.